Okay. Good afternoon. I'm John Kosmatka, Director of the California Space Grant Consortium and a Professor of Structural Engineering here at the University of California, San Diego. I'd like to thank you all for coming. We have a very special seminar co-sponsored by the California Space Grant and the Arthur C. Clarke Center for Human Imagination here in our brand new Structural and Materials Engineering building. Our guest speaker, Brian Schratz from the NASA Jet Propulsion Laboratory, or JPL, in Pasadena, California, will present an overview of NASA's Mars Science Laboratory mission, entry, descent, and landing telecommunications, and his first-hand account of working in mission control on the night Curiosity landed, which you will see is the most complex landing ever attempted on Mars. First, a little background about Brian. Brian received his engineering degrees from Penn State, first a Bachelor's of Science in Electrical Engineering with honors in 2006, and a Master of Science in 2008. As a student, Brian was active with Pennsylvania's Space Grant Program, where he co-founded the Student Space Programs Laboratory and developed instruments for several near-space balloon, sounding rocket, and satellite projects. He was a summer undergraduate research fellow at both NASA Langley and NASA JPL. In the summer of 2006 at NASA JPL, as a senior, he led a group of 20 fellow students to develop a mission concept for a Mars payload. Brian is a member of the Tau Beta National Engineering Honor Society, the Eta Kappa Nu Honor Society for Electrical and Computer Engineers, and a fellow of NASA's Graduate Student Research Program. Brian is currently a telecommunication systems engineer at JPL and is focusing his research efforts on developing microwave instrumentation for the next GRACE mission, which is mapping the Earth's gravitational field. He is actively mentoring NASA undergraduate research fellow. When he is not working, he also enjoys backpacking, mountain biking, skiing, and sailing. It is really an honor for us to have Brian here with us today. Please join me in giving a warm welcome to a young and tremendously accomplished engineer, Mr. Brian Schratz.
Thank you very much. It's a pleasure to be here. Thank you very much to the Space Grant Consortium for having me. Before I start, I just want to give a thank you to Space Grant. So I came from Penn State, and the Pennsylvania Space Grant is the reason I'm here today. They were able to sponsor the sounding rocket, balloon, and satellite programs that John mentioned. It gave me an incredible amount of experience. I learned things I would never learn in the classroom, and it gave me the skills of managing and leading students, prepared me for working at JPL. So without those experiences, I wouldn't be here. So definitely thank you very much. And actually, the center picture is myself and another Space Grant student at JPL that unveiled Scarecrow, which was the engineering test model for MSL back in 2005. So yeah, thank you, Space Grant. Great job with that. So before I start, I want to sort of step back and do a preface for why MSL is here. And really start with a fundamental question that really propels a lot of what JPL does, and that's, are we alone in the universe? Or even more specifically, could life exist, or has it existed in our backyard, in our solar system? So when you start thinking about the idea to go back to school and ask some fundamental basics, what causes life, or what makes life happen? So some obvious things, the major building blocks of life, the chemical compositions, energy, either from the sun, or as we've seen on our own planet, the depths of the ocean in total darkness, thermal vents of the ocean floor can support life as well, even without the sun. Water for liquid chemistry and a habitable environment. And the picture here is from the Atacama Desert, where they found microbial life in otherwise barren wasteland. And there's also more physical things. The size of the planet, is a huge gas giant. Is it in an area within the sun where you're not going to burn up like mercury? Do you have time for life to start, or other question marks? And it sort of brings us to Mars. So we know Earth, warm, wet, a nice thick atmosphere and a magnetic shield to protect us. Looking at Mars, currently at least, it's cold, mostly dry, although recently we've now discovered there's water ice as well. Very thin atmosphere, and there's our magnetic fields, but definitely not the global one. They're more locally sporadic. But a lot of people still think that Mars is one of the best chances we have for finding life itself, or existence of past life, or even if the building blocks of life are there. Not to say that there aren't other options out there. JPLs have robotic explorers to every planet in the solar system. There are places, the methane lakes or methane seas of Titan, the underground, or the sub-ice liquid water oceans of Enceladus. There's lots of places out there, but Mars being our neighbor and our closest analog is a prime target. Which brings us to sort of MSL and all its little members of the family. So the recent missions of Mars have discovered that the surface actually reveals a diverse and dynamic history, looking at evidence of, or previous evidence of sustained water, rivers, deltas, and in the past was probably a much more warmer, habitable environment with liquid water flowing, which is very exciting. The first mission to Mars showed a very, very dry desert, and really a lot of emphasis was taken away from Mars. We thought it was dead, and the more we look at it, the more we realize there actually was a lot of interesting stuff there. So the orbiters, Odyssey and MRO, and the European Space Agency's Mars Express have taken pictures of beaches that look like liquid water. But to really get a close-up look, you have to go to the surface. MER has, between Spring and Opportunity, found lots of evidence of liquid water and taught us a lot about the surface of Mars. The Venus went to the pole, and MSL is the next step in that process. And what MSL brings us is a much more capable laboratory, an order of magnitude in mass, more science we've ever done on the surface, with a lot more capability. So it's capable of exploring a local region, not just a small area. So MER was sized for a 3-month mission, although we've somewhat beaten that warranty by 8 or so years. At least one of them. So where MSL is designed to drive for kilometers, not just a few meters. With an RTG power supply, it's going to last for years. It has in situ chemistry labs. Right on board, we can do samples and analysis of Mars material right there. So very capable, but we also want to go to the right spot, and that sort of brings us to how you land something like this. So to start, sorry. There you go. So to give you a sense of scale, and a shameless plug for myself. So we have Mars Pathfinder 1997. Pathfinder because it was the first time we've ever landed something with wheels on Mars. It was JPL's going to get their feet wet and really trying some new things out. This little 25-kilogram microwave-sized rover with little met stations and cameras designed to go meters. MER in 2004, incredibly successful missions, 175 kilograms. Borrowed a lot of the entry, descent, landing technology for Pathfinder. And then we said we want to do more. So we want to go to more interesting places, we want to do more science, we want to do more, and that requires a much bigger rover. So you can see MSL is definitely the bigger of the three brothers. 900 kilograms compared to 175 for MER. Incredibly complex mission, and to land that takes a lot. So I said we want to go to somewhere fun, because we land in the middle of the desert, that's not so exciting. So many scientists around the world got together and decided where the best place to go would be. And it's hard to see, but there's a little yellow circle up there, and that's Gale Crater, and the landing site specifically in Gale Crater. You can zoom in a little bit. You see, so this is Mount Sharp in the middle, Gale Crater on the outside, and this yellow circle is the landing ellipse where we plan to land MSL. To give you a sense of scale, because we're looking at abstractness, this compares Gale Crater to a few analog Earth mountains. So not quite as big as Everest, but it's definitely bigger than Mount Rainier. So we're talking a very, very, very large mountain. And from orbit, we've actually seen that it has very interesting scientific promise. So looking at sulfates and silicates, a lot of things to show evidence from orbit at least of liquid water, and possibly signs of habitable reasons for life to exist. But again, without going to the surface, it's really hard to tell. Give you an appreciation. So I was saying, size is a big difference, but also accuracy. I like this picture because it really shows what we've had to grow from. You have the Viking orbiters and landers back in the 70s, and you have to give them a lot of credit because we knew nothing about Mars, or very, very little at least. So we actually sent 2 pairs of spacecraft. Each of them had an orbiter and a lander attached. They entered orbit first and did recon, and we learned about Mars first, and then found a place to land. But we knew very little about the atmosphere, we knew very little about dynamics and how it changes and how it affects landing. So our landing ellipse was huge. We just didn't know a lot. When you get down to Pathfinder, you know, for learning more, spirit and opportunity even more, and you know, having new technology that helps us get better. But you know, curiosity. Avionics that we only use in cruise, solar panels to power all that stuff, which is not used on the surface. We throw this away before we come in. The entry vehicle is an air shell, the back shell, and the heat shield down here. Our descent stage or rocket pack, and then the rover itself folds up and sits right underneath it. So this was a picture. I think this is actually at JPL before we shipped to the Cape. So you see the rover stowed up with the bottom of the belly pan. With the wheels, the landing radar here, and then the back shell behind it. This is testing at the heat shield and the back shell, and then I like this picture just because it looks really cool. But showing the landing radar above the rover, from below. I don't want to spend a whole lot of time going into details, but it's interesting to know sort of what EDL is. So I'm going to go through spend a little bit of time on sort of a crash course in the landing on Mars. So as I mentioned before, about 10 minutes before entry, we separate the cruise stage, and it just falls into the atmosphere and burns up. It did a great job getting us there, but it's no longer useful to get rid of it. Before landing, actually, how many aerospace majors in the room? Aero heavy. I can't talk. But, so I brought show and tell. So before we actually enter the atmosphere, we actually eject these tungsten weights that offset the center of gravity and gives us a little bit of lift. And by firing thrusters and rotating the vehicle around, we actually modulate where that lift is. So we can lift up, lift down, left, right. And one of the biggest things that gives you its large landing lifts is this uncertainty atmosphere. So we have IMUs, inertial measurement units, on board the spacecraft, which are just dead reckoning at this point. Like on cruise, we're using star trackers, but on the cruise station, that goes away, IMUs are all you have. So it's measuring, the accelerations, the velocities, the rotation rates, and figuring out where it is. And we tell it where we want it to go. And so it has its reference trajectory. And it looks at, cross-range and downrange errors and steers the spacecraft to actually sort of fly out the errors. And that gives a lot of capability to get it on much tighter orbits. So we separate the balance mass deployment, CVMD, whatever. We hit the atmosphere. So coming an hour or so before, and it was actually terrifying for us in mission control because we had this little simulation like showing us how fast we're getting. And a few hours before, going 8,000 miles an hour relative to Mars, slow. But as we start getting closer and closer, the effect of gravity starts pulling you in. So this velocity number on the screen starts clocking up and faster, and we hit the atmosphere about 13,000 miles an hour when we're pulled in. So obviously it's a little toasty. The heat shield will actually warm up to about 3,000 degrees Fahrenheit. And then we'll decelerate rapidly, reaching about 12 Gs on the vehicle. And while going to hypersonic, this is when the thrusters are actually firing. So we're engulfing this fireball and going very, very fast and slowing down quickly and steering at the time. And the capsule actually is sort of flying left or right and banking back and forth. So we burn off the vast majority of energy just in this stage, and we're still going supersonic. And so about 8.5 miles up, still going about 1,000 miles an hour, we deploy a parachute. So it's a 70-foot parachute. It's the largest we've ever deployed on Mars. There's actually a sample of it down here if you guys want to touch it afterwards. Not the real parachute, obviously. We have 8 test parachutes we built for wind tunnel tests and whatnot. And let us cut one up and bring it around. Sort of sad, but you get to touch it, so it's okay. So the parachute, takes us from going pretty much horizontal and starts slowing you down, to the subsonic region and tipping you over vertically. While going about, I think 300 miles an hour, we deployed a heat shield. Remember, at this point, we're still just dead reckoning off of the IMUs. But to land, that's not good enough. So we have a landing radar we brought with us, but with the heat shield on, it's a giant lens cap. So, again, heat shield done its job, but got to get rid of it. So 300 miles an hour, we blow the heat shield off and let the landing radar start looking for the ground. It turns out it actually required much earlier than we thought. During testing, this is where we died a lot. So during, usually for the record, for testing reasons, like the test hardware didn't work, the radar is actually very good. But a lot of things, just personally, there's a lot of emotion in the set. So when we saw that it acquired the ground, it was a very, very big moment for a lot of people in the room. So after the radar acquires the ground, it will stay locked on and at a certain altitude, in this case about a mile, still going about 200 miles an hour. The parachute is not going to slow us down enough because there's not a whole lot of atmosphere on Mars to do it. So we cut the parachute back shell loose and we fall out, and then ignite 8 landing engines to fly us down the rest of the way, and that's the rocket pack. As you get close to the ground, about 60 feet off the ground, the rover will separate from the descent stage on these 3 ropes and be lowered to the ground. The mobility will deploy. The rover will hit the ground gently at about 2 miles an hour. The descent stage will feel that and then fly away and crash in a really awesome explosion. We had 100 and some kilos of fuel on board afterwards on pressurized tank. So when it hit hard, and you can tell. So we'll get to that later. So EDL in a nutshell. Now you're all EDL engineers. Congratulations. So my role, as John mentioned, was responsible for EDL telecom. So what that is sort of multifaceted. The first step is making sure that the telecom system is working during EDL. So the flight software is doing the right thing. The hardware is being configured by flight software correctly. So the radios are all working. And that the information we want is coming out. So the full data set of EDL is like 100 megabytes of data. We have a kilobyte per second link, which is not a lot. So there's no way you can get it all out. So we have to pick and choose what we want to send. And you want to send it quickly, because if bad things happen, you don't know until a minute later. There's no point. And then to all assets. So we have Mars orbiters that can relay data for us. We also are talking directly back to Earth. So we need to work with those teams to make sure that they're also ready to listen to us as we're transmitting. Sort of like the tree in the woods analogy. We transmit and they don't listen. Pointless. If they listen, we don't transmit. Equally pointless. So it's sort of a very orchestrated event. The point of EDL telecom, or EDLCom for short, is actually mandated by headquarters because some of the previous Mars missions, trying to save a few bucks, opted to not have any kind of coverage during EDL, and we lost a couple missions back in the 90s. And it's very, very hard to tell why, because you say do EDL and then you turn off everything and you hope to hear from it on the ground. The only worst thing than losing a $2.5 billion mission is not being able to tell anyone else why and make the same failure again. So we are required during all critical events, so in this case landing, for other missions, orbit insertions, launches, things like that, to have a constant communication with the vehicle to make sure we know what's happening, and if things go wrong, figure out why. On a good day, it has the added benefit of supplying a really cool show for everyone in the world to see. So we did a good day, obviously, and we got some really cool video out of it. So to give you sort of a picture view of what the whole orchestration looks like. So as I mentioned, we have orbiters around Mars. So the Mars Reconnaissance Orbiter and Mars Odyssey are NASA orbiters. And the European Space Agency has Mars Express. So each of them were listening in their own separate way. Mars Odyssey was a real-time link. It's capable of receiving data in real time, turning around almost immediately and sending it right back to Earth over X-band to what we call the Deep Space Network, which is a collection of 3 stations around the world, 120 degrees apart. So you can, no matter where the Earth is pointing, we have a station in view. And then they send it back to JPL for all of us to see, then we send it out to the world. In this case, Australia was the site that was in view, so all of our data went through Canberra in Australia, relayed back over our dedicated lines to JPL, and then out to all the news trucks. Mars Reconnaissance Orbiter, it's a newer satellite. 2001 was Mars Odyssey, 2006 was MRO. It has a more capable rover or radio, and what we actually do is we record the data. But instead of trying to, how many EEs in the room now? Questions? 2, 3. Wow, bad advertising. So people like where you can either record it, demodulate in real time and strip the data out, or you could just record the raw spectrum. So we actually just record the raw signal, don't bother trying to get the data out of it, and send the entire file back. So it's like a 900 megabyte file after landing, which definitely can do in real time. But in the event of weird dynamics and things happening, you can do a lot with that signal and really pull out the raw waveform. So nothing in real time, but a lot of information afterwards. MRO also has a high-res camera, which takes the cool pictures of us on the parachute. And Mars Express actually was in a weird orbit and just records the carrier. So we can see the carrier moving back and forth. We can't actually pull data out of it. It's also worth noting, so we do a lot of tests, many tests, as I've told some people already today. And we do something called operational readiness test, where we pretend it's real. So we all sit in mission control, and we have ground versions of the orbiters, and we actually transmit from MSL and send them over lines to other buildings to JPL, and we put Doppler and attenuation on the signal and make it feel very, very real. Turns out it's actually harder to fake it than to actually do it for real. So for all you think we faked the moon landing, trust me, it's easier to land it yourself. Because we did 2 of these big tests, actually 3, and never did it actually work, like telecom. Some rack crapped out, or something broke, or we got some wires crossed, or someone changed a variable in the ground software that made everything not work. So I did a very good job of setting the bar incredibly low for landing day. So myself, I was terrified because we never actually made it work when it counted. Other tests, when no one else was watching, it worked all the time. But when the whole world was watching, it never worked. So I was nervous, to say the least. Again, it worked nicely. So if you watch like the live feed, you can see like myself, the telecom guy, getting really excited. Everyone else is bored out of their mind because we got like 1 bit of data. We're like, yes! I'm done. I'm out. See you guys later. So more you Aero guys in the room. EDL with the orbiters and the ground is a very orchestrated ballet. So to make sure things are all in the right place, we calculate our reference trajectories, we give them to the orbiter teams, we tag up once a week and make sure that they're doing the little burns little by little in the months before EDL to just nudge their orbiters in the right position. So we see here is, so we have Odyssey coming down north to south, we have MRO coming south to north, and MSL falling in right behind Mars, going west to east. And Mars Express is on this elliptical orbit, like way out here and going that way. So this is what it looks like at entry. You also notice that this blue vector, which is sort of hard to see on the screen, is the Earth vector. You can see it sort of pointed a little bit away from where we are. And about halfway through EDL, between the heat chill separation and the back chill separation, is when we lose direct contact to Earth. So the orbiters still have the link because they're higher up, but we actually lose our direct to Earth signal halfway through. The good news is that the direct to Earth is very good for covering sort of slow happening events. Actually, I meant to talk about that earlier. We only send tones. So during cruise, we can do like up to 25 or 50 kilobits per second on the surface. We can do, actually don't even know on the surface because I never cared. But during EDL, because we're lower gain antennas, there's lots of uncertainty dynamics. The best we can do is we send tones. So carriers at different frequencies, if you mix it down, literally it sounds like someone's playing a keyboard 1 note at a time. And each of those tones means something to us. So we have 255 different tones out there, and depending on what tones come out, it says the vehicle is doing certain things. So nominal events, it goes, okay, cruise state separation, balanced mass ejection, return to entry, spinning down, et cetera, et cetera. Actually, spin down, turn to entry. But and then there's also faults, like our power system's crapping out, or we failed to get a lock, or we're banking way out of all of the bad tones, which we didn't see any of, luckily. And then at entry, so you see the orbiters were phased so that, that's it. Yeah, so MRO is right on top of MSL. Odyssey is sort of on top, but a little farther east. MEX is way gone, and Earth is also completely gone. So what Odyssey looked like in real time, and if some of you watched the live feed, you saw screens like this. It's something we tried for the first time on this mission. So we have a lot of data coming back, and even though it's it's 1 kilobyte per second, we actually squeeze a lot of information into there. There's 150-ish telemetry channels for like subsystem state. We have a bunch of high rate telemetry coming down. High rate is like a hertz, 2 hertz, so not very high rate, but for us it's pretty big. It's 150 million miles away, gives a break. We said, well, rather than looking at these little plots and waveforms, why don't we just send it to a visualization computer and have it tell us what it's doing? So we actually route the data directly to another computer our graphics guys put together, and it renders in real time. So on the left side, you see the different states, the guidance, navigation, and control software algorithm, what state turn around left or clockwise, counterclockwise for the bank reversals. You see parachutes come out. The dials on the bottom give you a nice view of like how much fuel we're using, how fast we're going. And actually on landing day, this was useful because I had like 4 different screens I was looking at. In hindsight, that was dumb because there's no way your brain can process that much information that fast while having like just pumped up on adrenaline. So halfway through landing, we had one of the big plasma screens in the control room. I just said, forget it. I'm turning around looking at the screen because I know that this shows the stuff I really care about, and we'll look at the rest of it later. Because it was so much, it was information overload. We couldn't look at it that much. So that was very, very useful. And Odyssey did a great job of getting us that data. Also, this is one of our bonus goals. A few of us thought it'd be really cool to get a picture on the surface, just because we'd like to be the first to do anything. Justifying it with we have a couple minutes of coverage after touchdown. We want to see the state of the vehicle. When we are done, there's a whole team of service people that are waiting to take the vehicle over and go about the mission. And we asked them, what would be the best way? Oh, sorry. This one. So what would be the best way to know, in a minute or two with a very small amount of data if we're healthy or not? And well, if we can send a picture and we're not there's no wheel 40 feet from us, we're probably in good shape. So okay, so we'll take a picture. So we actually rigged it up. After all of the critical events right after touchdown are done, we kicked off a sequence to actually operate the HazCams, hazard avoidance cameras on the rover, to take a picture and send it back. We were not sure if it would actually, it might have not actually worked for a few different reasons, which I'm not going to go into. So 50-50, the cameras actually would have worked in that environment at that time. And then the coverage might not have been there either. So HazCam pictures were a total bonus. And again, it worked. It was just a really weird day that everything went the right way, and all of the craziness and testing never happened. Another reason we really wanted to is that we thought maybe, just maybe, if we're really lucky, we could actually catch the descent stage in its final moments of life. This was a long shot goal. There's no way we'll ever get this. The odds have to be everything has to go right. So sure enough, we got the pictures back. You see, there's a lot of stuff all over, and we actually fly the cameras with clear lens caps to protect it from the dust that gets kicked up. And then we have little pyros that blow the lens caps off later. Just in case the pyros don't work, they're clear, so we have something. So there's a lot of dust on the lens caps, and then there's this weird little splotch in the middle, and it sort of looks like something interesting. These are stereo cameras, so it actually takes a picture from left and then from a right, and you overlay them. This is sort of averaged out, but this is definitely still there. Then we took a picture a couple hours later, and we call it Sol 0, the 0th day of the mission, and there's nothing there. So we were pretty sure at the time that that's actually the impact cloud from the descent stage flying away and smashing into the surface and exploding. We have photogrammetry, which is sort of the analysis of photographs and measurement by that. For JPL surface missions and some other stuff we do, we have some very, very good people. And they estimate that this was, I think it was 80 to 100 by 60 to 80 meters in size. We're talking a very, very massive cloud of dust and hydrazine. Just give me an idea of MRO. There we go. So this is a simulation of MRO flying the trajectory for EDL, and you'll see it to the top of the screen. MSL will start coming to view in trajectory, and you'll see how the spacecraft actually has to turn and point to capture MSL, during that event. And we gave it a 50-50 chance of the camera actually lining up. The nice thing is that the UHF antenna that's listening to MSL is co-aligned with the camera, so by aiming it to talk, for telecom to work, the camera's freebie. So we gave them a range, we think that between here and here we have a pretty good chance of seeing it, so take a picture there and we'll cross our fingers. So after landing, there's a local establishment that offered to stay open for very, very late, so we all went there afterwards. Like a grocery store or something. Oops, sorry. My bad. Here, I'm trying to find my mouse. Oh, whatever. I'm going to skip around a little bit. There we go. So we were all, having a good time, and we got this email that from the camera guys. They got this picture. This is a real picture from MRO during EDL. So, and I don't know how they found this so quickly, because these pictures are monstrous, and it's a little speck. I think they must have had a bunch of interns or something standing by, dividing the pixel by pixel, because their response time is incredible. So they're able to do little photo cleanup, and you can clearly see this perfectly inflated parachute. There are videos on YouTube, I think, or if not, they're around there somewhere on the web, where some parachute tests that did not go so well, where it never actually inflates, or it just deploys and shreds. So again, this is the biggest parachute we've ever flown. We sort of took the previous one and scaled it and did some math and hoped that it was correct, and did some testing on it, a lot of testing. But again, to really fly it on a Mars environment, there's really no way to be absolutely sure. So this was excellent, and the soft goods guys, as we call them, the parachute people, were thrilled. I mean, to see their creation, actually working on Mars was phenomenal. From a telecom side, so actually, I figured that I didn't want to do work after landing, or would be able to. just because we hadn't slept in a while. I actually set a computer up to monitor the downlink and then process all this open loop telemetry that came back in real time and send me a picture on my iPhone, so I wouldn't have to do any work. So not too long after the parachute, we get this picture back. So unfortunately, for the aero guys, we do just EE stuff, so just sit back and think about changing majors. This is a spectrum. So if you've ever heard an ambulance pass by, it's low, then it gets higher, or it gets compressed, and then it goes away again. It's just Doppler effect. So what you see in this picture is this is the carrier signal from MSL as recorded by MRO. And you can see it, this is us creeping into the atmosphere, accelerating, getting faster and faster and faster and faster, and then bam, we hit the atmosphere and start slowing down rapidly. This giant ugly mess is what we call plasma blackout, which some of us didn't think would actually happen. On past missions like Phoenix, we saw brownout, and what's causing it is that this fireball engulfing the vehicle, there's actually, the air is breaking down into plasma and interrupting our communication. So you see like Apollo 13, same idea. So we saw this, and it was unambiguously, destroyed. There's no way we would have gotten the signal through, and it turns out Odyssey didn't really lock up until we got, out here. So from a telecom standpoint, that's really cool. And you can also see, just to be sure, we threw in a couple like carrier pulses and things in the signal, and that's all these black lines are. So you can see in the spectrum, like all the software worked, everything timed out or happened exactly when it should have. Parachute deploy, you see a lot of spreading around here, and then after touchdown, the orbiter setting, the signal goes away. So looking at my iPhone and seeing this picture, I can tell pretty much in an instant like how well we did, and like everything looked nominal. So it's a pretty cool picture. MRO afterwards also came back and took a lot of pictures of the ground. So we basically made a mess of the surface. But it's impressive that they can actually see from orbit, evidence of everything happening. So again, this is a heat shield before, as you saw, and then also on the surface later. We have the heat shield. This is not MRO actually. We have the heat shield actually impacting. This was taken from the Mars Descent Imager. It's a camera mounted on the bottom of the rover that was taking video on the way down. The whole video is on YouTube. Definitely worth watching. And then of course is this. So this is the descent stage. So you see it impacted here, and then stuff flew all over the place. There's even some dots over here where stuff really got ejected. It's hard to tell what that was, but something very, very big happened. You're talking hundreds of meters of this stuff like flying through the air. So we left a pretty good scar. EDL guys would love to go take a look at this. The scientists are like, we're not going anywhere near that, so we'll probably never see it up close. And then, of course, the rover itself. So this is actually a couple days after driving. So you see the landing site was here, the scours from the descent stage plumes, cleaning off the surface, and then we drove a little bit of ways. So it's really cool to be able to see where we are on Mars from something else other than us. And just because it's cool, again, this is one of the first few shots from the Mars Descent Imager showing the heat shield after deployment. This is not photoshopped or computer rendered. This is an actual picture from the rover of the heat shield falling away. And you can see the white spots are actually just targets to wide balance targets for the imager, so we know the color is right. It's hard to see in this picture where so Medley is actually up here. There's an instrument monitoring the heat shield performance. We put right on the heat shield, measuring temperatures and pressures of the heat shield. So the Medley guys were excited. It's like Mars EDL instrumentation, Medley. So to actually see your hardware again is really cool. I think there's rumors that people actually signed the heat shield and they shouldn't have, and you can see it if you look closely. But oops. So a lot of people ask, what was it like to be, in the room on that day? Remember, we've been testing for years, and a lot of the testing is actually being very evil, trying to think of everything that could possibly go wrong, and breaking the vehicle intentionally to see how it reacts. Even going to extremes as pulling cables out like during EDL, and like whoops, gone, and making sure the vehicle responds correctly. So a lot of us have been, you sort of get skewed in your thinking to get very, very paranoid. So even though like the likelihood of some of these things happening are like insignificantly small, like, some epsilon, in your mind they're just as probable as things that are more credible. So it's hard to sort of forget all the things that can go wrong. And I like to tell people you should watch the video because you can see who worked on what based on how they react. So we have the navigation guys waiting for the navigation solutions to be correct. Getting very relieved that it works. Keith is the flight director. This is actually towards the end, so he's just waiting for the whole thing to work. But Keith has incredible knowledge of everything else in the rover too. So he was watch his face, you can pretty much tell everything that's going on by his face. And I think this was actually on YouTube like a minute and a half after it happened. And my buddy actually emailed it to me. And we threw up on the big screen like, hey Keith, present. So it was this, every time something happens correctly, you get excited because it finally works. Like, there's 10 things you can stop worrying about forever. And then you realize that in about 3 seconds, something just as terrifying is about to happen. So it's this emotional roller coaster of like, yes, it worked. Oh no. Yes, it worked. Oh no. I think a lot of us just had nothing left towards the end. So for myself and the telecom working, which is actually a pretty quiescent part of EDL, relatively, was phenomenal. When we first got that data, it means MSL UHF was working, means Odyssey was working, means the DSN was working, and all of the DSN routing to the Odyssey ground ops, to the MSL ground ops, and uncoding and unwrapping and piping it out. All of that worked, which again never happened before. So everyone else was quiet, and Peter, the other telecom guy, and myself were like hugging each other in the aisles. And it's like yes, and really just thought about going home after that. And just to give you sort of a feel, I think this is on the web.